Hello and welcome to section 3.5, where we're going to be talking about Venn diagrams and in particular, how to use Venn diagrams to solve probability problems. So here's an example of a fun Venn diagram. The set on the left is candy, the yellow set. That's candy. The set on the right is corn. And of course, in the middle is our candy corn. One more. Here's a three set Venn diagram about pancakes. Things are that uses egg are in the yellow set. Flour is in the kind of purplish set, and milk is in the blue. And you can see the overlaps. Where all three of those things overlap, you get pancakes. So it's just a kind of a fun reminder to what Venn diagrams are. So a Venn diagram is a picture that represents sets, and we can use it to represent outcomes of an experiment. So for example, thinking about probability, let's roll two die and we're going to add the results of the two die together. What are all of our possible outcomes? Remember, this is what we call the sample space. We talked about that in the 3.1 video. Here's our sample space, right? We could have a 1 and a 1. We could have a 1 and a 2, a 1 and a 3, a 1 and a 4. So these are all the possible outcomes. And if we started writing our sample space, we could write it as a set as S. Oops, that's not what I wanted to do. S equals the set. Well, the very smallest sum is 2, right? That happens when you have a 1 and a 1. And then you could get a 3 by adding them together. And you have a couple different ways of getting that. You could get a 1 and a 2 or a 2 and a 1. Then you could go 4, 5, 6, 7, 8, 9, 10, 11, all the way up to 12 is the last possible value if you roll two sixes. So this is our sample space for the experiment of roll two die and add them together. So remember, events are sets of possible outcomes. So let's make up two events from our sample space. Event A is going to be that the sum is less than or equal to 6. So that's going to be the sum is less than or equal to 6. It shouldn't have a 1. I don't know what I'm thinking about there. You can't get a 1. Let's cross that out. You could have a 2, 3, 4, 5, or 6. And I can erase the 1 right there too. Maybe I can't. We'll just cross it out. And the event B is that the sum is even. So you could have a 2, 4, 6, 8, 10, or 12. So if we're going to put this experiment results into our Venn diagram, here's our set A, and it has 2, 3, 4, 5, and 6. And event B has 2, 4, 6, 8, 10, and 12. And so we put that all in set B, and then the overlap between the two are 2, 4, and 6. That's both less than or equal to 6 and even. And then there's a couple numbers that weren't in either of these. So we have 7, 9, and 11 outside both the sets, because while they're in the universe, they're in our sample space, which is the whole rectangle. Those three values aren't in set A or set B, so we just put them anywhere. We didn't have to write 7 above and 9 below. You could have written them anywhere in that white space inside the rectangle. All right, so let's go over a little bit of vocabulary. Union. So A union B is this, we use a symbol, it looks like a little U, kind of a wide U. A union B, it's all the elements in A or in B or in both. So if we're talking about A union B, I'm going to shade everything in A and everything in B. So that's A union B, and anything in those inside those sets would be an A union B. So both of those guys together. Sort of the opposite of that in one way, if you want to think of that word, is the intersection. And we use this little kind of upside down U. I think of it as an N, because I think intersection, and to me it looks like an N. A intersect B. And this is all the elements in both A and B. So that's going to be this space right here. If they're both in set A and in set B, then they're going to be in the intersection of A and B. And for example, in our last example, those were the numbers that were less than or equal to 6 and also were even. All right, so for our set, if we wanted to find A union B, we would write down, this is the set. Well, get rid of my 1 again. I don't know what happened there. 2, 3, 4, 6, 5. So 2, 3, 4, 5, 6. Those are all the guys in A, plus we add in 8, 10, and 12 to get all the things in A or in B. If we want to write intersection A and B, remember those are the values that are in both A and B, and those are just going to be 2, 4, 6. Right, so that's union and intersection. Another vocab word is A not, and we say that not A or A not, and these are all the elements that are not in A. This one has a lot of notation for some reason. You'll see A with the hash mark. You'll see A with a little C. Sometimes you'll also see A with a bar over the top. That's another one you sometimes see. In our homework, you'll probably see one of these two guys. Okay, they both mean not A, the complement of A. So things that are not in A. So if we're going to draw a picture of that, we draw a circle around A, right? Everything. Draw our A circle, put a little border around it. That's how I like to think of it. And then we color everything that is not inside that circle. All of this is not A. All right, so if we look at our example, and again, let's just cross out this one because I really drug that along. Our example, not A, would be all the elements not in A. So if you think about A, and I'm going to draw a little circle around it again. Here's A. What's not in A? Well, 7, 8, 9, 10, 11, and 12 are all not in A. Not in A. Numbers greater than 6, right? If we think about it in words. You don't have to put the numbers in order in a set. This would be the same as if I wrote, oops, I didn't mean to do that. This would be the same as if I wrote 7, 12, 8, 11, 9, 10. It doesn't matter what order you put them in. I just like to put them in numerical order because it's easier for me to keep track of what I have written down. All right, so let's practice by combining these a little bit. What I want you to do right now is I want you to try and shade in. So just draw this Venn diagram on your paper right now and shade in what you think will be an A intersect B, and then that set complemented, that set not. So not in the intersection of A and B. So pause the video and figure out what you think that will be. All right, well, are you back? The way I like to start these type of problems, I like to think about what is A intersect B and draw a circle around it. So this is A intersect B, this dark shaded spot. And if I wanted what was in A intersect B, that would be in here, right? A intersect B. But I want not that. So I want everything else. Anything that is not in the intersection of A and B. All right, let's do another practice problem. All right, I want you guys to give this one a try. We're going to take A and we're going to union that with the complement of B. So we're going to take A, we're going to take B complement, B not, and find their union. Pause the video and give that a try. All right, did you get that done? Let's go over this together. Whenever you're looking at a union, if it's part of it, you get to shade it in. So first thing I'm going to do is I'm going to shade in all of A because I know it's unioning something. So if it's in A, it's going to be in the final set. So I'm shading in all of A. All right. And now I'm going to shade in all of B naught. So B naught is all this. And that is A union B naught. It's all the shaded part. So we could even draw a border around this if we want to think about that. Sometimes I think drawing a border helps. And all that is outside the border is A union B naught. All right, let's learn a little more vocabulary. Sometimes when there's a lot of elements in the set, it's more convenient to talk about how many elements are in there rather than listing the specific elements. So we're going to go through and we're going to do an example of this. So the first thing I want to introduce you to is notation. It's kind of like a function, n of A, and it tells you the number of elements in A. So if A has 10 elements in it, then we would say n of A equals 10. If B has 12 elements, then n of B is 12. And it gives us some extra information. A and B share 6 elements together. So that would be, there's 6 in the intersection of A and B, and there are 30 elements in the entire set. So we're going to try and label the Venn diagram with this information. So sometimes when you're working, you like to start at the top and work down, but that doesn't really work very well for these types of problems. So I'm going to start with A and B share 6 elements. So I know that this space right there is 6. So that's what's in A and in B, the elements they share is 6. Now I'm going to go back up. So I used this one, check. And now I'm going to go up to this one and it's going to say A has 10 elements. So the whole thing, if A has 10 elements, 6 of them are in B also. 6 of them are in this shaded area. So I know that must be 4 over here. All right. So 4 in A, but not in B. 6 in the intersection of A and B on the first one. And if B has 12 elements, it has 6 already written down here. So we need 6 more over here to get to 12. Right. So 4 in only A, 6 in their intersection, and 6 more in only B. Finally, it tells us there are 30 elements in the entire set. Well, so far we have accounted for 16. So we need to figure out where 14 more are to get to 30. So there must be 14, neither in A nor in B, like outside in the white area, outside the blue circles in the white area. All right. So this is how you label a Venn diagram with number of elements. This doesn't mean the element 4 is an A. It means the number of elements in 4 are an A. And this is a little bit confusing, and you really have to just go by the context of the problem to understand what if we're talking about a specific element, the number 4, or if we're talking about number of elements. So how can we use Venn diagrams to compute probability? Well, remember the probability of an event occurring is the number of elements in the event divided by the number of elements in the sample space. So the probability of A is the number of elements in A divided by the number in the sample space. Remember, that's all the possible elements in the set. Well, if we look at A, there's 4 that are only in A, but 6 that are in A and B. So that's 10 total that are in A. And how many are in the sample space? Well, remember from the previous problem, it told us 30, but we can add them up too. 4 plus 6 plus 6 plus 14 is 30. So the probability of being an A is 10 out of 30, which is 1/3. I like to reduce my fractions. Please do not write 0.3. Those are not the same. That's not okay. So we're going to Ghostbuster that guy. If you want to write 0.3 repeating, you could do that. Or if you want to write approximately 0.33, that's also fine. But don't say that that equals 0.3. All right, I want you to pause the video right now, and I want you to figure out what is the probability of B occurring. All right, did you come back? Well, there's 6 and 6, so 12 total elements in B out of our 30 in our sample space. So that's 12 out of 30. I think 6 goes into both of those. So 2 out of 5. And you can write that this is equal to 0.4 because it is equal exactly to 0.4. All right, so that's the probability of Z, 40%-ish. 40%, sorry, exactly. If you want to write that as 40%. And the probability of A, you could write as 33 and 1/3% if you wanted to. Percent, decimals, fractions. I'm not super picky. The homework will tell you exactly what it's want. I'm not super picky as long as it's accurate. So don't round. All right, let's go ahead and use the label diagram to find these probabilities. The probability of not A, the probability of A union B, and the probability of A intersect B. Again, I want you to pause the video right now and go through and see if you can figure out these probabilities. All right, are you back? Well, let's figure out what's not A. Okay, well, A is here, right? That's A. Not A is everybody else. So there's a 6 and a 14. That's 20 out of 30. So that's 2/3. What about, let me just erase that circle. What about the probability of A union B? Remember, A union B is all of A and, well, that kind of swooped down a little bit farther, all of B. So there's 4 plus 6 plus 6, which is 16 things out of 30 in A union B. Let's see, I think that might be 8/15. And finally, A intersect B. Well, that's this guy right here. So that's 6 chances out of 30. 3 goes into both of those to be, 6 goes into both of those. 1/5, right? So hopefully you were able to use the Venn diagram to calculate those probabilities. All right, now we're going to use Venn diagrams to talk about conditional probability. Conditional probability is one of those topics that it can be a little complicated, but I think using Venn diagrams really helps. So we have some new notation here. It says the probability of A, and then it has a bar, and then B. And this means the probability that A happened, given that we know B happened. And it is called a conditional probability. Conditional meaning it depends on something else. So this would be like, let's say you rolled your 2 dice and you added up the sum, and then you told your friend, well, it's an even number. Well, then that would be like telling your friend that B happened, and now they have to guess. Now they have to guess what number was. If you told them it was an even number, they wouldn't guess it was a 7, right? So it gives them more information. It cuts down the sample space. So in this case, let's find the probability of A happening, given that we know the probability of B happens. So again, we rolled, this isn't the same example, but we rolled the dice and it said, you look at the dice, you know it's an even, you tell your friends it's an even number, what's the probability that it's less than 6? That's sort of what we're talking about here. Let's look at our example with this set of numbers. So if we know B has happened, okay, then we know we're somewhere in this set. Okay. So instead of being in the whole universe, the whole sample space, we only have 10 possible outcomes because we know that B happened. And that means we only have one of 10 choices. There's 6 things in A intersect B and 4 things that are not in A, but are in B. So instead of a sample space of 30, like before, we know B happened. So we only have a sample space of 10. So now if we're reduced to this red circle, what is the probability that A happened? Well, 6, right? Oh my gosh, I bumped it. 6. This is the number of elements that are in A and B. Divided by the number of elements in B. So when you're doing conditional probability, you look at this given information here, and that has now reduced your sample space. Instead of 30 outcomes, we only have the outcomes that happened with B, so that was 10. Within that circle, what's the probability of A happening? Well, it's 6 chances out of 10, or 3 out of 5. There's a nice formula for this. I kind of walked through the formula with the example, but sometimes people really like to use the formula. So here's a formula. You can put it in your note card. And it says the probability of A given B equals the probability of A intersect B over the probability of B. Let's go ahead and work through this formula. It's going to work out the same as the way when I just sort of reasoned it through. But the probability of A intersect B. Well, this is just regular old. There's no given. So we just need to find the probability of A intersect B. Well, we did that a few pages back, didn't we? Probability of A intersect B is 6 out of 30, or 1 out of 5. There's 6 in here, 30 total, so that's 6 out of 30. The probability of B, we already figured that one out too. We decided it was 10 out of 30. So the probability of A given B equals 6 out of 30 divided by 10 out of 30. If we remember how to divide fractions, we know that dividing by 10 30ths is the same as multiplying by 30 tenths. So 6 out of 30 times 30 out of 10. And now we multiply our fractions. We just multiply our numerators. 6 times 30 is 180. 30 times 10 is 300. So we have 180 out of 300. Let's reduce this fraction. Well, this one's kind of harder. So let's first divide by 10. That gets me to 18 out of 30. 2 goes into both of those guys. So that gets me to 9 out of 15. I guess 6 went into both of them too. 3 goes into both of those. 3 out of 5, which is exactly what we got last time, right? 6 out of 10, 3 out of 5, when we kind of just reasoned through it. So both of those ways are good ways to compute conditional probability. All right, I'm going to do one more example problem before I end this video. I know it's been kind of a long one. Suppose a basketball team had a season of 100 games, and with the following characteristics. 60 of all the games were home games, 25 of all the games were wins, and 20 of all the games were home game wins. So we need to find and interpret the probability of a win given home. And this is one of those problems where you have to do quite a bit of work before you can even start to work on the question they asked. The first thing we want to do is label the Venn diagram. Okay, we can't even start probability stuff until we label this Venn diagram. So it told us there's 100 home games. And remember, on these, you don't always start at the top. You start at kind of the most specific information. It told us that 20 of all the games were home game wins. So that means that there's 20 games that were at home and were also wins. Okay, so we did that one. 25 of all the games were wins. Well, 20 were home game wins, which leaves 5 to just be away game wins, right? And it says 60 of all the games were home games. Well, here's all of my home games. 20 were wins, which means that 40 were losses. All right, and this is the one that everybody always forgets. We have one more thing to label. We need to label the whole universe space there. We have 40 plus 20 plus 5. That makes 65, but we have 100 games, right? So that means 35 games were what would essentially be away losses, right? So we had 40 home game losses, 20 home game wins, 5 away game wins, and 35 away game losses. All right, so those are all our probabilities. What is the probability of a win given it was a home game? Well, let's go ahead and figure this out. If it's a home game, we're going to be in this circle, right? Got to be a home game. So instead, this is reducing our sample space. Instead of 100 games, we want to talk about these 60 home games. So that's our total. Of those 60 home games, how many were wins? Well, 20, right? So the probability of a win, given it's a home game, is 20 out of 60 or 1/3. That's kind of the reasoning way. We can also do the formula way. So the formula way says this is going to be equal to probability of win given home. I don't have a lot of space here, do I? Equals the probability of a win intersect home over the probability of a home game. Okay, so let's calculate these. The probability of a win intersect home game, well, that's this 20. Remember, this is the full way, so 20 out of 100 is the probability of having a win when you're at home, divided by the probability of a home game. Well, there was 60 home games out of 100 games. So we're going to take 20 out of 100 and divide it by 60 out of 100. So that's 20 out of 100 times 100 over 60, because dividing by 60 100ths is the same as multiplying by 160ths. This gets us to 2,000 over 6,000. Let's divide top and bottom by 1,000. It gets us to 2 over 6, which gets us to 1/3. So 2 different ways to calculate these conditional probabilities. Do whatever one works best for you, and good luck on this assignment.